Lesson 2 is properties of functions, and in 2.1 we're going to introduce domain. So before we get into the definition of domain, I want you to look at this picture over here. So a function, which we talked about in lesson 1, is kind of like a machine. So we have a function, and sometimes you'll see it's described as like a rule, which a rule is just kind of like describing what the function does. But we can think of the function as like a machine. And with that machine, we have values that we put into it. Those are called our input values, or just input. Put them into the machine or the function, and then we get values out. Those values that we get out are called the output. So now if we go to the upper left corner where the definition of domain is, it says the domain of a function is all of the possible input values or x values for which a function is defined. So next to input, I'm going to add domain. So the domain is kind of like a way of describing the set, or like all possible input values that we can put into the function, or basically put into the machine without breaking it. So like how this says for which a function is defined. Some functions are only defined in certain areas, so we can only put certain values in. Those values that we can put in would be the domain. Okay, so moving down here, a restricted domain can be created from a real life situation. For example, Gina opens a bank account with $100. Each week she deposits $20. This can be modeled by y equals 20x plus 100, where x represents the number of weeks since Gina opened the account and y represents the total amount in her account. And we want to find the domain of this. So you'll notice like up in the domain definition, I added that like the domain is all of the possible input values or x values. And when you have equations that involve x and y, x is going to be your domain. So that means that in this equation, all of the possible values that we can put in for x are going to be our domain. And underneath that, it says that x represents the number of weeks since Gina opened her account. So we want to think about, okay, does it make sense for x to be any number? Like 1 week, 2 weeks, 3 weeks. Yeah, those definitely make sense, but think about like, can x represent a negative number? If x is supposed to be the number of weeks since Gina opened her account, we can't have a negative amount of weeks since she opened her account. That would be like time traveling backwards. So in this case, we can only have x values that are non-negative, meaning they would have to be either equal to 0 for like that very start, or anything greater than 0. So we would write the domain with an inequality. X is greater than or equal to. So this is just greater than. And then the line underneath is or equal to 0. So that means that the domain, the possible x values for this situation of her opening her bank account, x has to be greater than or equal to 0, just meaning it can't be negative. You can't have a negative time frame. Okay, so moving down to the next line right here. When there's no context provided, like there's no word problem, kind of like Gina's bank account, many functions have domains of all real numbers. So we'll talk about what that looks like on a graph and in a function as well. So example 1, find the domain of each function. This little kind of like shaded area that I added in, that's going to be really helpful. So I'd make sure to write that down as well. So when we're looking at a graph, in order to determine the domain, we look for what are the possible x values, and then how far does the graph extend, left or right. Okay, so for A, the equation or the function itself is y equals 1/4 x plus 1, and that's graphed down below. So it tells me in that little shaded area, look for the possible x values. It also says look how far the graph extends from left to right. So if we look at our graph, you can see like it's going left forever. It's going like down and left, but it's going left forever. That's what the arrow is for. And then it's also going right forever. So nothing is going to stop that. So it's going to cover all of those possible like numbers. And how far it extends left or right is like how many x values it covers, because like if I keep going down to the like right, this would be like 9, 10, 11, 12 on the x-axis. So it's covering all of the possible x values. So we would write the domain is all real numbers. And domain is going to correspond, like I said, when you're looking at a graph, domain is x. So that's why it says like look for the possible x values on the graph. I would leave yourself a note down here that domain is x. That's something that like you'll eventually want to kind of have memorized. The domain is the x values on a graph. We'll learn about something in the next section called range. That'll be the y values. Okay, so there is a way of writing all real numbers like an inequality, kind of like what we had up here with x is greater than or equal to 0. So all real numbers is like every possible number, so it looks kind of funky the first time you see it, but you write it as x is less than infinity, which is like a sideways 8 when you draw it. I'm like pretty bad at drawing them, and greater than negative infinity. So this is just kind of like a tricky math way of writing all real numbers, every possible number from negative infinity, which is the smallest possible number, up to positive infinity, which is the biggest possible number. So it means the same as all real numbers, but you'd want to familiarize yourself with that way of writing it as well. Okay, and then for B, our equation is y equals x squared minus 8. So again, look for like the possible x values on the graph, or you could look at how far the graph extends left or right. So it's kind of hard to tell, but this graph, like it does start to go like up steep a lot, but it'll never go completely vertical. Like that would make it no longer a function because it would fail the vertical line test. So even if it's moving to the left like really slowly, it's still moving to the left forever. And same thing on the right. It's moving to the right like really slowly as it goes like up into the right, but it's still moving to the right forever. And so it's covering every possible x value. It's going left and right forever. So this would be all real numbers as well. And we'll do some that are not all real numbers, so I get kind of different versions of that. So all real numbers for domain. Remember, domain is like the possible x values. And then if we wanted to write an inequality, it would be x is less than positive infinity and greater than negative infinity. So the nice thing is like writing this, the way it's written will never change. Like these mean the same exact thing. So you can make yourself like a little sticky note or a note card that has like all real numbers on one side and the like x is less than infinity and greater than negative infinity on the other side. Okay, so one thing I want to point out before we move forward, we'll talk about this a little bit more later, but this for A, like that equation was y equals 1/4 x plus 1. That's an example of a linear equation because the highest power of x was 1. And then this was, I think I'm actually going to change colors because it's going to get kind of messy on the other side. So 1a was a linear equation because the highest power over x was 1. And then the like example 1b, y equals x squared minus 8, that was a quadratic equation because the highest power over the x was a 2. So if there's no context, these equations, linear and quadratic, will always have domains of all real numbers. The only thing that would change that is if there was like context provided, kind of like the Gina's bank account problem. Okay, so if we look at C, we don't have the equation for this one, we're just looking at the graph. So I'm gonna go back up really quick to what we were supposed to look for. It says look for, and I'm reading like above off here, look for the possible x values on the graph, how far the graph extends left or right. So if we look at this graph for C, it definitely doesn't look like the graph extends forever from left to right. It goes to the left forever, but there's this like stopping point right here. So that point on the graph is the point 0, 1, because to get there from 0, 0 right here, we don't go left or right, so that's why x is 0. We just go up 1, so that's why the y is 1. And that's kind of like our cutoff point for our graph. So we can't say x is all real numbers because it doesn't go to the right forever. So now we have to think about, okay, what x values does it cover? So it does cover, like, we do have one at x equals 0, because remember, points are organized like x, y, and there's a point at x equals 0. And then from that point, it goes to the left. So that covers all of the x values that are smaller than 0. So like -1, -2, -3. All those numbers are smaller than 0. So we would say the domain is x is less than 0, since it's covering all the numbers that are smaller than 0. And then the last thing that we need to look out for is whether or not this point right here is open or closed. If it's closed, it can be equal to 0. It means it can be exactly equal to 0 or exactly equal to that point. So we would put x is less than or equal to 0. So if you see, I'm going to add a little note here, closed dot is either less than or equal to or greater than or equal to, and then the open circle, you'll see that in future examples, is just a less than or a greater than, no line underneath it. So this domain would just be x is less than or equal to 0. Okay, and then for D, you can see like this graph looks different because it's just a set of points. When you have just a set of points, this is actually called a discrete graph or a discrete function because it's not like a connected line. So our process is a little bit different for this one. I would say when it's discrete, you're focusing more on like this part, the possible x values of the graph, not how far the graph extends from left to right. So to find the possible x values for the graph, we have to find all those points that are on the graph. So we'll just go through and list each one. I'm going to zoom in because it's kind of small. So like for the blue point, I go right 2 on the x-axis and up 1, so that's 2, 1. For the green point, I go right 3 on the x-axis, right here, and then up 4, so it'd be 3, 4. For the purple point, I'm going right 5, and then I go up 6, so 5, 6. For the black point, I go right 7 and then up 5, so 7, 5. And then for the red point, I go right 9 and then up 3, so 9, 3. And then going back to that like look for note, we're supposed to look for all of the possible x values. So we need to find all the x values from these points. So remember, points are organized like in order x, y. So I need to find all the numbers, the first numbers from each point. So 2, 3, 5, 7, and 9. And then we're just going to list them in order of smallest to largest. So we would do 2, 3, so 2 from the first one, 3, 5. Then the next one would be 7. And then the next one would be 9. We wouldn't just write like 2 through 9. We would specifically list each number from each point, each x coordinate from each point. So 2, 3, 5, 7, and 9. And then we like bracket our list in these kind of like funky curly cues. It's called a set. So the domain is the set of 2, 3, 5, 7, and 9. Okay, so moving down to 2.2, so we have our same little like function kind of picture up here where we had our input, that was the domain that we put inside the function or the machine. It goes inside the function, it does its thing, and then it spits out and gives us the output. The range, which is the title of 2.2, is the set of all possible output values or y values of a function. So that's the definition of range. The range of a function is all of the possible output values or y values of a function. So down here under output, I'm going to add range. So finding it is really similar. It works the same way, it's just domain is x, range is y. I recommend writing that in like as many places as possible because that's one of those things that like you're just going to be expected to know at some point. So domain is the x values, range is the y values. Okay, so example 1, find the range of each function, we have another little like look for box. So look for the possible y values on the graph. And then this time, since we're looking at y values, which like tell you how far up or down to go on your point, we're not looking at how far the graph extends left or right. We're looking at how far the graph extends up or down. So that part does change. Okay, so for the first one, example 1a is y equals 1/4 x plus 1. It's the same equation from the last section. And this time we're looking at how far does the graph extend up or down. So like you could see in the right corner, like this graph is like trending upward. It's like up and to the right, but it's still going like up forever. And then over here it's going down and to the left forever. So it's going up forever, down forever. So if it's going in both directions, up and down forever, it would be all real numbers again. So range is all real numbers. And leave yourself a note that the range is the y values. And that does change the way we write it as an inequality like a little bit. Instead of x being in the middle like we had up here, I didn't go far enough. Up here, we had like x in the middle of our inequality because domain is all the x values. For range, we're going to have y in the middle. So it would be almost exactly the same, but y is less than infinity and greater than negative infinity. And that means the same thing as all real numbers, because that's saying that, you know, y is less than the biggest possible number, infinity, but greater than the smallest possible number of negative infinity. Okay, so for example 1b now, y equals x squared minus 8x. So same equation as like in the last section, same exact graph as well. This time we're not looking at how far the graph is extending left and right though. We're supposed to be looking at how far the graph is extending up and down. So we can very clearly see like this graph is definitely going up, but it's not going down forever. It has a low point down there at the very, very bottom. So if it has a low point at the very, very bottom, we can find that point. So to get to that point, let's see, let me just actually put the point on there and not circle it. It's right here. We don't go left or right at all from the origin, from right here. We just go down 8. So that point would be 0 and then negative 8. So 0 and then negative 8. And then we want to think about, okay, it kind of goes back to like when we talked about max versus min, maximum or minimum. We look at the height of that point, or because range is specifically the y value, we look at the y value from that point, which is negative 8. And then do we go like up from that point or down from that point? So since our y value negative 8 is like the lowest point on the graph, that means that our range must be all the y values that are greater than negative 8. And then we want to think about, is our function exactly on that point on negative 8? And it is, it crosses through there exactly. So even though there's no dot there, it crosses through it exactly. So that means it can be equal to negative 8. So we would put y is greater than or equal to negative 8. Since that negative 8 is kind of like the very bottom, and this means that our range can cover any y value that's from negative 8 or above it or greater than it. And that would be all the values up here. Okay, so moving on to C, this one should look identical as well as the last section, but we're finding range, we're finding something different. But this one's kind of nice because the approach is exactly the same. We need to find each point. So I'm going to go through and label each point again. The blue point, we go right 2, up 1. So that would be 2, 1. The green point, we're going right 3 and then up 4. So that would be 3, 4. The purple point, we're going right 5, up 6. The black point, we're going right 7, up 5, so 7, 5. And then the red point, we're going right 9, up 3, so 9, 3. And then same thing as last time, this is still called like a discrete graph where all the points are separated. They're not really like connected. So when it's a discrete graph, we want to actually just look for like what are all the possible y values specifically. So we'll look at each point and find each y value. Remember, y is going to be the second number in the parentheses. So it'd be 1, 4, 6, 5, 3. We want to write them like in order though, of smallest to largest. So if we start with our smallest, that's 1. So 1, and then the next one would be 3, because we're just looking at the y values and we're ordering those. So if you want to like go from smallest to largest, you can start at like the lowest point and then work your way up. So the next one would be the 4 from 3, 4. And then the next one would be 5 from 7, 5. And then the last one would be 6. And then we close it in those kind of like curly brackets. And then with these ones, I think it's really worth your time to just double check to make sure you didn't like miss any of them. So, oops, I erased too much. Okay, so 1, 1, 3, 3, 4, 4, 5, 5, and then 6 and 6. So we're good. We got the y value from each point, and we got them in order from least to greatest. So range is the set of 1, 3, 4, 5, and 6. Okay, so this little graphic before we start 2.3 is just kind of like a quick little like note as far as if you are finding domain and range from looking at the equation. So like on these examples, we looked at the graphs to find the domain and range, and this is if you just have an equation or the function itself with no graph. So I'm going to add a little note or a star. This is for no graph. Okay, sorry. So for when you have no graph, so all linear functions, when there's no context, like, Gina's bank account, but all linear functions always have a domain and a range of all real numbers. Linear functions, here's some examples of them, are when the highest power of x is 1. So x to the first power. Really, you won't see an exponent over the x is what it would be. Or like this is 2x to the first power. This is a 1/3 x to the first power. But these like first powers, those are what make it linear. And then moving on to the next side, so for all quadratic functions, again with no context like Gina's bank account, they have a domain of all real numbers. They will have a limited range though, but if you were asked to find it, you would be given a graph. So the domain is all real numbers for any of those. And quadratics are ones that have the highest power of x is 2, so x squared, 4x squared, 9x squared, with the other terms all having exponents less than that. So the fact that they have x squared as their highest power of x, meaning like there's no x to the third power or anything like that, that's what makes these quadratic. So that's what you would look for if you were just given the equation or the function itself. Okay, so moving down to 2.3. So 2.3 is all about function notation, which it looks kind of scary at first, like the first time that you see it, but it's not as bad as it seems. So function notation is just a special way of writing functions. So up until this point, we would see them written as like y equals 5x plus 4. Function notation takes that y away and it replaces with this like f parentheses x, like that. It's not how you read it. I'll tell you how you read it in a second. But everything else stays the same. Like the 5x plus 4 stays the same. It's really just these that get swapped. Okay, now heading over here, this is how we read it. So the f with the parentheses x is read as f of x. So when you see me read or hear me read f of x, that's what I'm saying. And then similarly, like g with the parentheses of x, it would be called g of x. So you read the like first letter and then whatever's in the parentheses you say after of. So like f of x, g of x. Or like, for example, if I had like technically functions can have any name, so I'll just give you a few like random examples. Like if I had g of c, that would be g of c, like that. Or like h of k, h of I hit the up arrow, sorry, I was afraid that would happen, but it would be h of k. So it can be any letter inside or like outside the parentheses, but you always read it as the first letter first and then the word of and then the number or the letter inside the parentheses second. Okay, so I'm going to go through this last little part and just kind of label like what each name is here of f of x equals 5x plus 4. So that part I would write like kind of big on your paper because we're going to go through like each little section. So you may want to like kind of have enough room. Okay, it doesn't have to be massive, but anyways, so f, like just the f, is the name. So like the name of the function would be f. And then the like x is the input. And then f of x, like the value of it, which we're going to learn a lot more about this, is going to be the output. So it's totally okay if this doesn't mean like that much right now. We're going to get much more comfortable with function notation. And then the 5x plus 4 is called the rule. So kind of the process for evaluating functions, and again, we'll do it in the future, is like we put an input in for x. It also goes in the rule, and then we simplify the rule, and then it gives us the output. So f, like that number in the letter in front, that's the name of the function. X is the input. Those two together, like the function evaluated for the input, would give you the output. And then the 5x plus 4 over here is the rule, and that can change as well. Okay, so biggest thing from this section is just finding domain and range. Main thing I would like you to remember, like no matter what, is that domain is the x values, range is the y values.